To discuss the domain of a function and finding it algebraically, we're going to focus on three types of functions. The functions we're going to be focusing on are polynomial functions, rational functions, and also radical functions. And once we see the strategies for these three types, it's really going to help us when we're finding the domain for any kind of an equation. So first of all, let's recall that the domain is simply the collection of the x values that are in the entire set of ordered pair solutions, right? So remember, a function is a collection of ordered pairs, and we just want to see who all the x values are in that collection. Well, the problem is that there are infinitely many of them, and so when we think about this from an algebraic perspective, we need some tools. So let's kind of take a look first of all at a polynomial function. So for example, a polynomial function is one where the x's are located in the top of any fraction, and any of the powers on the x's are positive integers. So that's what makes it a polynomial. So in order to be considered an x value that is part of the domain, we need to consider all of the x values that are going to generate real outputs, right? Put another way, we want to find all of the x values that are going to generate outputs that are real. If we have an output that is real, then we're going to have a point that is graphable. So the output being real tells me that the y value is real. We are also needing for the domain elements, or the x values, to be real as well. If we have a real input and a real output, this gives us a graphable point on our Cartesian plane, and the x values that cause that to happen are going to be part of the domain, and the y values that we get out are part of the range. So both the x's and the y's have to be real in order to be considered part of the domain and part of the range. Therefore, any x value that I plug into the function that makes the output not real, that's not going to be part of the domain. So a not real value or a not acceptable output would have been, like, let's say, a negative under a radical where we get an I or an imaginary number. Any x value that causes that to happen is not part of the domain. Any x value that causes me to have 0 in the denominator, which is undefined, that x value would not be part of the domain. We need outputs that are real and defined. So the cool thing about polynomials is that these x values are being raised to the integer power. That means none of the x's are under radicals, none of the x's are in denominators, and really, any x value that I plug in is going to give me a real output, right? There is no x value that's going to cause that quantity to be undefined or this quantity to be imaginary. I could plug in x's or zeros, I can plug in x's or negatives, and nothing is going to cause my output to be anything other than a real number. So what that means for us is that the output on a polynomial is always going to be real, and that tells us that this x value can be anything. Any real x value is going to cause an output that is real, and therefore the domain, which is the collection of all the x values, is always going to be negative infinity to positive infinity. We don't have any restrictions on what x can be because every single x value is going to generate a real output and a graphable point. So the domain of a polynomial is all real numbers. When we get into rational functions, we're going to have to be a little bit more careful. A rational function is going to have an x in the denominator of a fraction. And if there's an x in the denominator of the fraction, what we're going to be watching out for is any x value that caused the denominator to be equal to 0. Because if we have a denominator that is 0, then we're going to get a quantity that is undefined, and if undefined is the output, we're not going to get a point because we can't graph an x value with the y value that is undefined, right? This is not a graphable point. So we can't have undefined as an output, and we would want to eliminate any x's that cause 0 in the denominator. And so that's what we want to watch out for and exclude. So we see here in this rational function that the x value -4 is the one that would cause the output of the denominator to be 0. So that's the x value that we cannot have in the domain. Therefore, our domain is everything else. And how do we say everything except for -4? We would say negative infinity to -4, stop and start with -4 to leave out only that one value, and then from -4 to positive infinity. So this would be the domain of that rational function, leaving out the problematic x value. Now, the third type of function we're going to look at is a radical function, and here we're going to have x value underneath the radical. So if we have x plus 5 underneath the radical here, this is a radical function. And so what we want to watch out for are negatives under the radical, which is another way of saying negative radicands. So the radicand is basically everything that is underneath the radical. If we ended up with an x value that caused the radicand to be a negative number, then the output would be imaginary. And if the output is imaginary, we're not going to be able to graph this point, right? Because if we have an imaginary y value, that's not something that can be graphed. So we would need to leave out any x value that causes this radicand to be negative. So what we want to do here is we want to figure out who are the x values that keep the radicand a positive number. That's the requirement. And therefore what we're going to do is take the radicand and figure out who are the x's that make it stay positive. So let's grab up the radicand, x plus 5, set it greater than or equal to 0, and say who are the x's that make this positive? Well, we can just solve it for x. X is going to be greater than or equal to -5, and these are the x's that I'm allowed to plug into that function. These are the x's that make up the domain of this radical function. So we would say it in interval notation that we start with -5 and go off to positive infinity, and we would be including the -5 because if x is -5, let's take a look at that, what would the function output be? -5 plugged in is going to give me 0 as an output, and of course 0 is a real number. That makes -5 a graphable point. The x coordinate is -5 and the y coordinate is 0. So -5 is part of the domain, and therefore we would include it with a bracket.